Welcome. In this video, we're going to derive the surface area formula using calculus. So the way we're going to do it is we're going to have a frustum, a circular cone frustum, where the frustum is called because you cut part of it. You cut it like that, and it's a right circular cone but cut. So that's a frustum. So the key here is that we have lines going on the surface of the frustum, and they can go infinitesimal. So you can let n equal infinity, and you arrive at this formula for when you revolve around the x-axis. When you revolve around the y-axis, like here, you use, instead of f of x, you use x. Okay. So remember these pictures. When we revolve, when the function is revolved around the x-axis, then we call this average radius is going to be f of x, and when we revolve around the y-axis, it's going to be x. So let's derive the formula. So it's very similar to the arc length formula in a way. You're gonna see why. So how can we? So because we have the small radius, we call it R1, and the big radius, we call it R2, and we're going from A to B. So we're gonna call average radius equal to R1 plus R2 over 2. And then the length of the line, Li, is equal to delta xi squared plus delta yi squared. And we know that the surface area of a frustum is equal to 2 pi r times L. But because we're going to approximate it, we're going to say this is approximate to. So one thing to notice is that by the intermediate value theorem, this average radius, this r, is equal to some di, where di is in the interval. So somewhere here we call it ai, bi. So di belongs to somewhere in the middle between ai and bi. So basically, by the intermediate value, because this function, the function here that we're going to be looking at, the functions, they're going to be continuous and differentiable on AB. That means that the intermediate value theorem applies, and that radius is equal to somewhere. So for each interval, the average radius is going to be the value of the function at some point between AI and BI. And then LI is this. So the approximation is going to be 2 pi f di L I. And then that's equal to 2 pi f di delta xi squared plus delta yi squared. And just like we did on the arc length formula, we can do this as follows: 2 pi f di delta xi squared plus delta yi squared of delta xi squared times delta xi squared. And that's approximately to 2 pi fi di. We pull out delta xi squared, so that's 1 plus delta y over delta xi squared delta xi. So to approximate it, we need to take the sum of all those lines around the surface of the frustum, or the function that we're looking at. So basically that is, so this is approximately equal to I from 1 to n of 2 pi f di of 1 plus delta I squared over delta xi and then delta xi. And then because of and just like we did on the arc length formula, because of mean value theorem, since the function here is continuously differentiable on AB, there exists a CI such that f prime of CI is equal to delta y over delta xi. So now the approximation becomes so let's pull out the 2 pi, then we let n of f of di of 1 plus f prime of ci squared delta xi. Now if we wanna get an exact answer, then we take s is equal to, so we let n approach infinity of the sum, And then I will let, because since the function is continuously differentiable, then we let this equal to the integral of 2 pi from a to b of f of x equal to 1 plus f prime of x dx. And there we have the function, the formula. But remember, this only works if the function is revolved around the x-axis. So this one here. But if we're revolving about the y-axis, then with this is equal to 2 pi, because from here to here is x. So here x. So 2 pi a over b x 1 plus f prime of x dx. And of course this is a square and this is a square. So these are the formula. And of course, if you have your function, this function in terms of y, all you have to do is change x for y. So solve for x in the function with the function, and plot and change x to y, and do the same integral, and you should get an answer. So you could do this formula in terms of x or in terms of y with the given function. That's all you need to do. So thank you very much. Don't forget to subscribe, please. It helps a lot.